Good morning to one and all. First, I would like to welcome all the team members of International Research Excellence Award. Myself, Dr. Syed Zamir, the Associate Professor and Director of the Research Center, Department of Mechanical, Hosea College of Engineering, India. Today, I want to discuss my research work on fatigue life estimation of artificial hip joint model using the finite element method. In our research study, I had tried to develop a new material, new artificial material, okay, which is new artificial material, which is a biocompatible to the human body. Because nowadays we are using the various metallic materials and various biomaterials, which lead to the drawback, the basically the mismatch in the stiffness of the material that leads to failure of the prosthesis material due to various reasons that we are going to discuss in the next slides. Actually, at present we have developed a new material, okay, and this material will be analyzed for the various activities of the human being in order to estimate the fatigue life of the component. Here we have developed what a polymer matrix composite material, wherein the matrix material we used as the ultra high molecular weight polyethylene with varying percentage of the reinforcement from 58% of the short E glass fibers to 48% of titanium dioxide. And also we use the Palgram linear damage rule in order to estimate the fatigue life of the component. And in the result we got the fatigue life, it is what less than, which indicate the component design, it is what safe. As we know, bone, it's nothing but what a composite material. Two-thirds of the weight, it consists of what the inorganic material having the composition similar to the hydroxyapatite, and the remaining molecule is nothing but what it's nothing but what the organic molecules, mainly the collagen molecules. And as I told, under excess loading or the impact, bone fracture. And fracture of this component will fracture of the bone will occur because of the crack size orientation, morphology, and the various loads acting on the bone. Here, whenever there is a fracture of the bone occur, here we'll go for different types. In that, one is there, that is total hip replacement. Total hip replacement, it's nothing but what a surgical procedure in which the diseased part or the fractured part we are going to replace and remove with new artificial material, which is known as the prosthesis material. See, the human being is subjected to what various activities like fast walking, standing, up and down, stair climbing, jumping, etc. See, these activities of the human being, it will result in aspetic loosening of the hip joint due to cyclic variation of the loads. That will lead to what? The damage of the fracture component, damage of the what? The prosthesis material. Also, one of the reason due to which the fracture of the hip joint will occur, that is because of what? Wear, corrosion, environmental stress cracking, okay, that is and the shear stress that will occur between the ball and socket of the hip joint. See, you can see this figure. See, this figure indicate here it's nothing but what a hip joint is nothing but what a composition of ball and socket that you can see it in the here in the figure. It consists of what? The ball and the socket. Basically, this component is nothing but what? The largest weight bearing joint. It composed of what? Rounded head of the femur and the acetabulum pelvis in a ball and socket arrangement. Now we have carried out various research, the literature survey, and whereas the various scholars, okay, they have studied on the different aspects. Basically, research in this area has been carried out on the cemented type of the joint, cementless joint, finite element analysis, experimental with design models, analysis on the cracked and fractured bone. And most of the researchers, they use the prosthesis material or the alternate material for the bone, as bone is the stainless steel 316L series, titanium 6Al 4V alloys, cobalt chromium alloys, high density polyethylene, hydroxyapatite, and the other coatings. Okay, and various authors, that is SH2 et al., they have studied the overall fatigue fracture problems associated with the metallic biomaterials, polymeric biomaterials, ceramic type of the biomaterials. And apart from this, Bergman, he is the most important research, which is also called what the father in evaluating the dynamic stress distribution and the bone. Okay, and also most of the authors like Sivasankar et al., Joy H. Jones, they have evaluated, they have studied the various aspects on the present topic. Now, what I conclude from the literature review of the various scholars as the hip joint prosthesis, modification, replacement, and transplantation is the solution for most of the problems in medical field for hip joint arthroplasticity. Most of the researchers are carried with respect to biocompatible material or using the stainless steel 316L series, titanium 6L 4V alloy, and cobalt chromium alloy as the material of the choice for hip joint prosthesis. Different failure theories are predicted in order to estimate the failure mechanism of what the hip joint implant material, and in order to increase the life of this implant material. And you can see here in the figure the damage whenever whenever the component got fractured, that is because of the rubbing movement. Okay, the fractured part, the femoral head, see they are going to cut. You can see here, this is the fractured part. Okay, that here fracture of the surface will occur because of what, the wear process, because of the rubbing movement between the ball and the socket. Or here the neck is cut off as shown in the figure, and the marrow cavity is made inside the femur, and the hip of the what are the artificial material they are going to use, that will be fitted inside by with the help of the PMMA cement, or with the help of what, a press fit method. And also you can see in this figure the hip, the total entire weight of the human body, because of the various activities, it will be subjected under this ball portion on this hip joint. And also you can see over here, and also you can see here the fractured component has been removed, and the processing material, the biocompatible material, generally here what you can see here in the figure, it is nothing but what, this stainless steel. Okay, it has been inserted inside of the human bone. And here when the load acts, see here in the downward direction, there will be a tensile and the compressive forces will be developed over here. Okay, because of these tensile and compressive forces, a small crack will be initiated inside of the processing material or the bone material. Okay, that will further, it will get it propagate and leads to the what, failure of the component. Here also you can see here the various components which are made up of what, different types of the biomaterials. The cup you can see over here, you can see here the cup, it is made up of what, the stainless steel. Okay, here you can see it is made up of what, titanium alloy. The polyethylene insert we are going to add in between, and this is what, the femoral head, which is made up of what, other biocompatible material. You can see over here the femoral head, which is made up of what, the high density polyethylene or some polymeric material. Now let us first discuss, before going on to the actual research, let us discuss the what are the reasons for the hip failure. The major reasons for hip failure are, it is subjected to what, failure due to what, bone loss, very important factor. bone loss of the bone because of what the rubbing movement. Okay, long term aesthetic loosening, that is also one of the important reason. Hip failure due to bone loss is caused by production of the wear particles associated with the deterioration of the prosthesis material. Failure due to fatigue loading, very very important point to be considered. Fatigue loading of the hip joint because of what? Normal daily activities, as I told, sitting, walking, stair climbing, knee bending, etc. Relative micromotion resulting from the improper implant fitting in the bone cavity, very very important factor to be considered. Okay, for the failure of the hip joint. And also the stress shielding. Stress shielding, it is nothing but what? Mismatch in the material mechanical properties, generally the Young's modulus of the processes material and the bone material. And also the excess stress cancellation near the implant is leads toward the transfer of the load between the stiff implant and the other component, that will finally lead toward the failure of the component. Now, we know fatigue is nothing but what? It's defined as the failure under the repeated dynamic or fluctuating load, okay, which never reaches a level sufficient to cause failure in the single application. That is, this is one of the standard definition of the fatigue. Failure will occur at a stress level less than the yield strength for a static load after a lengthy period of repeated stresses. And you know that there are three main methods in order to estimate the fatigue life of the component. One is called what? The stress life approach, strain life approach, and the crack propagation or the fracture mechanics approach. Here, what exactly is the biomaterial? A material developed to interface with what? Biological system. Okay, to evaluate, treat, or replace any tissue, organ, or functions of the body. Whereas the biocompatibility, it is the term, the ability of the material to perform with an appropriate host response of a living system to a presence of the material. That means biocompatibility means it is the ability of the material, okay, in order to adjust with the host body environment. That means the material should be what? Compatible to the human body. The whatever the artificial material we are going to use for the fractured component, for the hip replacement component, it should be compatible to the body. If the material is not compatible, that will lead to further reaction in the human body and automatically leads to what? Failure of the component and finally the death of the patient. There are different materials are available. Polymeric biomaterials are there, bioceramic materials are there, metallic biomaterials are there, biocomposites are there, and various synthetic materials like the metals, cobalt, chromium alloy, stainless steel, gold, titanium alloy. Okay, these are used for what? Orthopedic, fracture fixation, dental and facial reconstruction and distance. And when we are going to consider what this ceramic category, we are having the alumina, zirconia, calcium phosphate, pyrolytic carbons, and also we are having various types of the coating type bioglasses, hydroxyapatites, diamond-like carbon. It is used for the orthopedics in growth. And apart from this, we are having various synthetic biomaterials. And the what is the need for this biocomposite material? The need is first here the isotropic alloy used for the stem have much higher stiffness than that of what? The bone material. Almost all the implants are having what? 5 to 20 times more stiffer the whatever the biomaterial, the various metallic biomaterials what we are using, they are having the stiffness 5 to 20 times more than the stiffness of what? The bone. Okay, here that is why there is a mismatch. There is a mismatch in what? The Young's modulus of the material, that will lead to what? Stress shielding effect and the stress concentration, and finally leads to what? The failure of the components. Now here, apart from this, here in our project we have developed what? The process is the high density, as I told. We have considered, we have developed what? A biocompatible composite material, wherein we have considered the high density polyethylene as the matrix material, and varying percentage of the fibers, that is short e-glass fibers, and we have used what titanium dioxide in varying percentage of the reinforcement from the 0 weight percent to what 40 weight percent. Okay, then the components, what the composite specimen whatever we have developed through injection molding machine, we use what the injection molding machine. Okay, the components are obtained, okay, they are developed, they are prepared as per the ASTM standards in order to evaluate the various mechanical properties as well as the various tribological properties. And here we got what the optimized material properties in the 48% of the reinforcement component, wherein we are having what 48% of short e-glass fibers. The material properties obtained from the experimental results of optimized percentage of the reinforcement specimens, as we are going to we are utilize that material properties in order to evaluate the fatigue life of the component using the finite element method. For that, we have used what? The CATIA in order to develop what? The 3D modeling of the hip joint model. Okay, you can see it. You can see it here in the sketch. That is the complete model. Okay, has been developed. These are what the separate component. You can see here the cup component, the stem component. Whereas this is nothing but what the bone component. All are all what separate component. Then we have here you can see here in this sketch that is in the green color. Okay, this green color, that's nothing but what the artificial material that what has been inserted inside of the bone. Okay, and for this particular part, we have given what the mechanical properties related to what the experiment result of the result obtained from the newly developed composite specimens. And here the other component, nothing but we have given what the other properties, that is the bone properties, the different properties we have given for these assigned properties. Here for modeling purpose, for 3D modeling purpose, we have used what the CATIA, and the dimensions have been obtained by, we have considered further the CT scan dimensions of what an average age patient. The dimension we have considered, that we have collected through the literature survey. By using those dimensions, okay, we have developed the 3D model of the hip joint using the CATIA. Further, the meshing of the model has been done. Okay, the meshing of done, as you can see here, the meshed view, that is using the hypermesh software. Okay, then as I told, the material properties what we assigned, it is nothing but what the optimized material properties what we obtained from the fabricated specimens of hybrid composite material, that wherein we are having ultra high molecular weight polyethylene as the matrix material, and 48% of titanium dioxide particles which will be of what size of 0.22 micron meter size, and 58% of the short e-glass fibers. For this composition, we got what the optimized mechanical properties, optimized material properties. The optimized material properties you can see it here in the table, wherein here we got, you can see over here. Okay, the bone, it is having the cortical bone, it is having what the Young's modulus of what 15,000 MPa, whereas what we got it is what 7,500. Okay, and the Poisson's ratio you can see here for the bone is 0.3. What we got from the material is what 0.4. And then once the, you can see here, once the model has been developed using the 3D modeling software, and then we have done for meshing. Once this meshing is over, then we have applied what the boundary condition. For the boundary condition, okay, we have considered here, that is what the fixed boundary condition here. You can see it here in the sketch. And at the ball point, okay, here we applied what the load. We applied the load. Now, what is this load? For these various values of the load, we have considered with the work of previous literature survey of G. Bergman et al. Okay, what he has done, he has considered an average patient weight of 70 kg. Okay, and for the hips, for this from this experimental result of the Bergman, we have considered the various loads. Okay, for the various activities Okay, that is 1304 Newton, 1270 Newton, 431 Newton, and 1473 Newton. These loads we have considered separately for the various activities like fast walking, normal walking, knee bending, downstairs respectively. And also we have considered what and muscular force of 1937 Newton at an angle of what 40 degree to the proximal area of the bone. Here the load applied, you can see here what we have applied over here. What I am showing over here, the load has been directly applied to what the ball portion of the hip joint model. Okay, then we have done the stress analysis using the ANSYS software. Okay, wherein for result we obtained what for the fast walking condition we got what the 1304 Newton of the one Messi stress distribution. Okay, and 431 point Newton of the stress distribution for the knee bending case. And what we conclude from the analysis as fatigue analysis consists of what analysis of the load subjected to what hip joint due to various activities. A cyclic fatigue loading machine and also for the fabricated specimen we are subjected to what we have evaluated what the fatigue life for using the fatigue loading machine of 100.095 kilonewton capacity and having a strain range of 12.57 millimeter range, okay, which has been utilized to conduct the to evaluate the fatigue life for the fabricated specimen, wherein we got the SN curve, the endurance limit. What we got is 20.02 MPa, 02 MPa for our fabricated specimen. And what we conclude from the here the analysis as the plastic deformation and necking was not observed on the fatigue specimen during the testing. The shear zone of the specimen is what full of fibrous fracture phase and the shearing edges that indicate the propagation of the crack and fracture at the multiple location. That I will you can see it over here. This is what the SEM analysis of the what fractured specimen. The fabricated specimen is subject to what the fatigue to evaluate the fatigue load in the fatigue testing machine. You can see here the fractured component. Okay, the fractured surfaces. See what this indicate? It indicates the crack propagation will take place from the various locations. And this is what the SN curve obtained from the fatigue testing machine, wherein we got the endurance limit of around of 20 MPa that you can see it over here from the graph. And then also we have calculated what the numerically the what was the result we obtained from the experimental method, and also the result what we got from the ANSYS that we have numerically we have calculate using the stress life Goodman equation. That what you can see it over here. This is what the stress life Goodman equation. By using this stress Goodman equation, we have evaluated the fatigue life. Here we have used the material properties of what the optimize the material properties of the fabricated specimen, and the various calculation for the various terms you can see it over here been given in the table. And the number of cycles what we obtained for the various activities of the human being, you can see here in the table that is in the indicated as what n for the various activities we are getting this table. Finally, the life of the component we have estimated using the linear damage rule, Palmgren linear damage rule. Okay, the formula for that is for the various activities, that is each activity has been considered as an event. For every event, the first event, that means say for example slow walking, for that the corresponding the life of the component. Similar for the next activity of the human being, corresponding the life the n the fatigue life of the component. All those things we have considered, and the final result what we obtained is 3.045, which indicate that is less than 1. That indicate the whatever the load we have, that means the value can be calculated by taking the inverse of this the fatigue life what we got to 10 to the power of 5 cycle. That indicate the whatever the material we are developed, that is safe under the fatigue loading due to the various activities of the human being. Now let us I will come to the conclusion. Conventional biomaterial exhibits stress shielding effect due to the mismatch in the X amount of the bone and processed material. Okay, in this research study, ultra high molecular weight polyethylene as a matrix and titanium dioxide as the reinforcement, it has been successfully fabricated, and also we have used what short e-glass fibers, and it has been successfully fabricated as a processing material for hip replacement application. Material properties of the fabricated composite specimen were used to carry out the static and fatigue analysis of hip joint model using the finite element method. Volumetric stress distribution obtained from the static analysis results are used to calculate the stress distribution, okay, from the static analysis results. And finally, the life of the component was estimated using the linear Palmgren damage rule, and which indicates the component is safe under the design due to the various activities of the human being. The loads acts on the hip joint due to the various activities of the human being. Now, these are all what the various references what we have studied during the our research work. Now, if any